Thank you, Professor Reddy, and also the team of organizers. It's a great opportunity for me, and we are very proud that Professor Reddy is an alumni of IIT Roorkee, the institute which I'm working on for the past 4 years. I have listened to his presentation in IGC last year in Jalandhar as well, and also for an invited lecture in IIT Roorkee. So I owe my sincere thanks to Professor Reddy for keeping connections from the Indian academia as well, and also providing me this opportunity. This is a big platform for me. And thank you for your kind introduction, sir. I'm just starting my foots into the like a disaster mitigation research at IIT Roorkee, having my experience in engineering geology and geotechnical engineering disciplines. So this is the topic I choose for today. I have just seen the topics that was presented by previous lectures given in this webinar. Was very happy to have one more landslides that is also presented by an Indian practitioner from SDMA. So we know that every monsoon season we have this hydrologically triggered hazards in the Indian Himalayas. So those are actually like, let's say, shallow landslides. Just a moment, let me also. Uh, those are actually shallow landslides, debris flows, and also like potential large-scale flooding. And whenever we look into these hazards, it is always named as like 2013 North India floods, also the recent 2023 North India floods, and then the recent debris flow disasters that happened in Dharali in 2025 last year. Though these are floods, there is a main hydrological component and control of this. What comes with this flood is actually the debris material. So it is the sediments which is actually present in the hill slopes that get transported due to erosion, instability, and it comes to the river. And along the flood, the sediments actually causing a lot of damage. So all these problems are like sediment-related disaster. And we are in a bigger need to understand the triggering conditions of this disaster in order to inform, or if we could. Yes,
I was wondering, you are still on the title slide?
Yes, sir. Yes, sir. Still on the title slide.
Okay. Thanks.
Yeah. So the potential upscaling of the understanding from the minor scales is necessary. That's what we are going to see today through the presentation. So this is the presentation outline. These many of us are already aware about the problem statement of sediment-related hazards, with specific reference to the Himalayas, and then the scale of these studies, because these are happening at different scales. Let's say catchment scale, slope scale, territorial scale. So at what scale we need to address these problems in order to have a physical appraisals of the physical process that is taking place. And then the second part will touch upon the assessment. What my little experience in IIT Roorkee after joining this institution, at what scales that my research group here in Uttarakhand have approached this problem. So that is the assessment part. Then the detailed laboratory scale characterization, and we found something that we can upscale, because studying everything in the laboratory, though it is fundamental and very essential, we need to have a kind of understanding which is beneficial to the people in order to inform before a disaster happens. So we need to look into the technology which will give us an upscaling of the component that is developed from the lab to the field back, because the disasters are happening in the field. And we have a test application, though it is something like 13 years old. We are still working on this problem in order to get the meteorological as well as hydrometeorological thresholds that will develop into an early warning system. So that is how this presentation will go today. So the sediment-related disaster, this is a term that is widely applicable and accepted in the Japanese academia and disaster management disciplines in Japan. So what comes to the flood, as I already said, either it is a rainfall-induced landslide or a debris flow, those materials are actually transported to the river. And those sediments are actually causing damages to the infrastructure as well as human lives. So, for example, the 2013 Uttarakhand flash flood, if you search for it in Wikipedia, it is widely known as the 2013 North India flood. and as well as the largest debris flow disaster that happened in India, that is the 2024 Wayanad debris flow that happened in the Western Ghats. All these are sediment-related hazards where the control or component of hydrology is predominantly important. And we need to understand the fundamental hydrology as well as the geotechniques of the hazard in order to give some early warning information. Similarly, the 2021 Rishiganga Roorkee avalanche-induced debris flow and flash flood, it is a kind of cascading hazard. Though it is a debris flow that originated from a cold region, so the impact was in the down reaches where the impact of the sediments have actually caused the damage. Similarly, last year, August in 2025, the Darali and Herschel debris flows that happened in a catchment in the basin of Uttarkashi. So in the basin of the Bhagirathi river, close in the Uttarkashi district. So those are also like a sediment-related disaster. So these disasters are happening every year, mainly during the monsoon season in the form of rainfall-induced landslides, debris flows, and flash floods. So these are happening at a larger scale. For our understanding of the physical processes, there is a bit of bigger challenge, especially with reference to the Himalayas. If we look into the scale of any Earth system science study, if we put the unit of length in meters, so we do have from the nanoscale, microscale, mesoscale, and then the laboratory scale, the slope, catchment, and territorial scale. So the slope is where the geotechnical engineering is practiced. The catchment is where the hydrological sciences is practiced. The territorial scale is where the disaster management authorities will need to make their decision. So whenever these hazards that happened in 2013 and the other years, so it was not a single landslide happened. Even in the case of the Wayanad landslide or the Darali one, so it may be like a single to many number of landslides, but the impact was more. In 2013, there was more than like 6,000 landslides happened all across Uttarakhand. So that's what happening in the Himalayas, the abundance in numbers of these individual hazards. So we need a system that is operational at the regional scale in order to warn the people. So currently, we do have existing early warning systems in India by the National Landslide Forecasting Center, GSA, Kolkata, and they are giving a very good early warning of rainfall-induced landslides as well as debris flows. And the system is operational at the selected districts and it is experimental in selected districts. To do this, to do the hydrometeorological based or meteorological based early warning of the sediment-related disaster, we need to understand the hydrology. So we have to narrow it down to the catchment scale in order to understand the fundamental hydrology of the debris flows per se, rainfall-induced landslide or runoff-generated debris flows. And if it comes to the rainfall-induced landsliding, so there are techniques what many geotechnical engineers are aware of. It's this slope scale monitoring, where we already put some sensors in the slope, where we know that there is a problem of this landsliding that can be forecasted using the displacement-based thresholds. But the bigger challenge what we have in the Himalayas compared to other mountain ranges is the presence of complex materials that is all over the hill slopes. So we have to reduce even further down the scale. So as per fundamental geotechnical practice, so we have to do fundamental laboratory test in order to understand the processes. So what we do here in IIT Roorkee, also fundamental geotechnical tests that any geotechnical lab will do, and also reduced scale flume experiments where we actually scale down the problem in order to understand the triggering processes and all. We do have another scale what the advanced geotechnical laboratories across the globe are into, that is the mesoscale studies on biogeotechnics. So my group, or I'm not into this biogeotechnics, but there are some many studies are actually looking into the kind of biostructural mitigation practices for slope stabilization and all. So that's not going to be part of my presentation. I'll be talking with the scales from the laboratory to the catchment. And we do have a problem of reducing complexity because as we increase the scale, the human ability or as well as the computational efficiency of analyzing a problem becomes multitudinal. So we have to give up some kind of complexity or simplify the problem in terms of the phases of matter as well as in terms of the dimensions. But that also may have the increase in the uncertainty as we move from the fundamental scale to a larger scale. So we have to have the adjustment of addressing that uncertainty as well. In addition to it, if we scale down, if we draw a two-dimensional diagram of the physical processes that happens during a rainfall-induced landslide and debris flow, we go back to the fundamental soil mechanics textbook. Okay, in case of a saturated soil mechanics textbook or unsaturated soil mechanics part. So we go to the textbook. What the textbook tells is the hydrological processes that happens in a slope. So we do have the supply of this moisture flux boundary condition in the form of, let's say, rainfall. And we have this wetting front advancement that actually happens because of the infiltration. And when the unsaturated soil, because of the advancement of wetting front infiltration, converts into a saturated soil, there is also a loss of shear strength. That's what the fundamental understanding of a unsaturated soil slope stability problem tells us. And if we note down the variables that changes with the time in these physical processes, they are rainfall, that's the precipitation flux boundary condition. Then we do have runoff, infiltration exceeded runoff. Then we have saturation, the water level or pore water pressure, and then the shear strength. And these variables can be monitored with the sensors of different types such as rain gauges and until the acceleration. So if these variables are sensed, or if we can develop some index of some variables like rainfall, saturation, or something kind of a number which tells us over a larger region that this is what the situation of the variables is going to be in the coming hours, then we can actually use them in early warning system. That's why we are trying to further narrow down the processes for specific hill slopes in the Himalayas. And if we have like a continuous rainfall infiltration, then the infiltration exceeded runoff will actually erode further material that is available in the hill slope. So those are getting converted into a rainfall-induced debris flows, as we have narrowed down in this figure. As long as the material is pure soil, so we do have a strong understanding of soil mechanics, and we do also have a strong understanding of rock mechanics. But the materials what we face, what we get in landslide deposits or any kind of sediment related hazards in the Himalayas, it's not pure soil or neither pure rock. In most of the cases, it is a mixture of soil and rock, where we have the larger particles or fragments of rock as well as finer materials of soil, in addition to the pore spaces that is available in any granular material. In this case, what we have in case of a debris slide, so that is a type of landslide as per the updated Vaughan's classification of landslide by Oldrich Hunger in 2014. A debris slide is a sliding type of landslide whose primary material is actually a mixture of soil and rock, that we call it as a debris. And in any debris flow deposits, we'll always have a mixture of soil and rock. And this becomes the problem because understanding of the behavior of soil rock mixtures, which actually the predominant material in the debris itself is lacking at the finer state as well as in the laboratory scale. So if we want to know the hydrological processes or geomechanical processes that is happening during an event of a rainfall-induced landslide or debris flow, we need to know how the material, which is a granular material of different grain sizes, is going to respond to a given boundary condition, that is the rainfall. So here are like different debris flow deposits that is actually characterized in terms of a normal grain size curve as per USCS classification. You can see through different years. So this sampling we did when during my postdoc time in China. So in addition to the sampling that is possible by us, so we do fly the drones to actually map the larger part of the sediments, and also some in situ sampling is done, and as well as some laboratory based sampling is done. If we see for debris flow mechanics, if you talk to a hydraulics person, the 50% grain size D50 or D85 is important because it directly determines the erosional power or the erosional power that is required by the water to actually transport the material. And if we see here, across many years after the 2008 Wenchuan earthquake, in 2008, the Wenchuan earthquake happened. There were a lot of this loose debris material that is actually introduced to the hill slope because of landslide. And those materials has been removed by subsequent rainfall-induced debris flows in the coming years. From 2010 to 2019, still those events are actually happening. And we can see the 50% of the grain size is actually more than 10 mm. Okay, so the conventional soil mechanics test will not be able to accommodate this many large samples into a testing system. So we need to find some alternative method. So there is a much available literature available for actually understanding the seepage as well as mechanical characteristics of the debris material. In addition to that, in the Himalayas, since we have these deposits all across the hill slope, wherever we go, we sample the material, the grain size material, we find the maximum of D50. In more or less, it's always more than 10 mm in the Himalayas. Whereas in the Western Ghats, since it is an older lithology and the much amount of erosion has been already happened, and because of good amount of weathering, we have much finer deposits in the Western Ghats, whereas in the Himalayas, it's the opposite. And from traditional unsaturated soil mechanics textbook, we know the role of surface flux boundary condition in terms of a soil. And we know that during a rainfall, the pressure regime goes from unsaturated to saturated. So you will have like positive pore water pressures in the above the groundwater level as well. We wanted to know whether such unsaturated soil mechanics principle is also applicable for the debris material which is present in the Himalayas. And this is a textbook derived volumetric water content functions. So this tells us above the water pressure, above the groundwater level, where the pore water pressure is negative, which means the matrix section is active. So there is a reduction in volumetric water content, which we call it as a soil water characteristic curve in like unsaturated soil mechanics. It is a water retention curve in hydrology and agriculture sciences. And we do have this relative permeability that is getting lowered as we move above the groundwater table. So when we have the grains as a mixture of soil and rock, whether will this hypothesis of a rainfall-induced landslide will hold true or not? Because if we want to use some numerical model which actually follows the traditional soil mechanics principles for modeling a rainfall-induced landslide, we need to know whether it is applicable for larger grains or not. So there is a lot of uncertainties in the studies what we do here also. But we tried our best to limit those uncertainties and to get an understanding. So the first study is a case study which we did for a rainfall-induced debris slide. That is actually situated in Uttarakhand in the Agla river catchment. It's a tributary of Yamuna river. So, and this is the location of the debris slide, and this is a Google Earth image photos before the landslide that took place. That is a debris slide because the material it's a debris, and then the type of the movement is a sliding failure as per the updated advanced classification by Oldage Kungar in 2014. And here we have the debris slide. You can see it is marked in like red color boundary, and this is a slide. It's not that much steeper slide. It has an angle of like 45 to 50 degrees. And the material, what it has was more amount of fragmented rock as well as some amount of fines. And we did some in situ test to know the in situ properties of the material, but much of the strength and the characterization of the material to be conducted in lab. So we brought some samples as per all traditional geotechnical engineer practice is concerned. And this is the index hydrological and geotechnical properties of the debris material which is sampled. And if you pay attention to the USCS classification, what we got is a coarse gravel, that is GW, and we do had a uniformity coefficient of more than like 40, which means so the grain says it's a beautiful curve. And in addition to that, so the characterization is done. What we have to do is to test whether the rainfall-induced landslide hypothesis or the theory that is applicable for soil landslide, whether it will be applicable for landslides where you also have a larger material or not. Okay, but traditional engineers or practicing engineers will be aware more than what we do. But what we have tried to understand from here is the behavior, whether during the rainfall, the theory of the movement from the groundwater level from the negative regime to positive regime, will it hold true or not? So we looked into the scaling laws that is available for reduced scale experiments in the lab. So of course, for any debris flow researcher will know about Iverson, and he has given the scaling laws. So this should be accounted if we want to do, if we want to mimic some natural processes of a debris slide or flow in the lab. And this is the in situ or the derived grain size, and also we have the grain size what we put in the flume experiment. We do have a typical limitation in our lab because we are using conventional geotechnical equipments, where for triaxial testing, of course, less than 5 millimeter grains only can be accounted, and we can do the direct shear test for to know the in dry conditions only, to know the shear strength of the material, that is cohesion and angle of internal friction. So what we did is we transported something like 2 tons of sample from the debris slide. So after the failure only we visited the site and we transported that material. And after doing this in situ as well as laboratory characterization using this different conventional geotechnical apparatus, so we moved to testing it using a reduced scale flume after getting to know the triaxial strength in case of for the finer materials only, as we can see here, there is an impact of apparent cohesion, not that much we could say for a sand or clay, but there is an impact of this angle of internal friction if we increase the matrix section as well. This comes from the unsaturated saturated triaxial test, and we did have a limitation in our apparatus that it can only consider matrix section of up to like 80 kilopascal. And we believed that is enough for our study because the slip surface depth of many landslides here in the Himalayas, what we observed is more close to like average of 5 meter. So in 5 meter, as per the Darcy's law, we kind of estimated that not more than 50 kilopascal for water pressure or the negative in positive, it's going to develop. So we found that this matrix section has an impact in the shear strength for the fine particles of the material. And in order to know whether the process understanding what we actually gain from the traditional textbook will hold through here or not, we did some reduced scale flume experiment. So this flume is actually designed with the support of financial support from IIT Roorkee, and this is the schematic of the flume. It has like three sections as well: 1 meter, 1.5 meter, and then 1.25 meter. So it is inclined in an overall angle of more than 45 degrees, and two sections it is inclined 45 and 35. We have the convenience of changing the slope angle as well. And our intention was to put the actual debris material which we see in the field, and then we fill the tank, the flume tank. And this is the parametric studies what we want to see for different rainfall intensities as determined from the India Meteorological Department's rainfall data. So this is the hourly rainfall, and as this is the parametric study that is schematicized for different rainfall intensities and as well as different initial moisture contents with the increasing slope angle. So we perform these 5 experiments, and each experiment is repeated 3 times in order to ensure the correctness and also to get the average. So this is the condition. And when this rainfall is actually given under different conditions, so we have seen in the 2-dimensional cross section that there are some variables which we can actually monitor from the field: the soil moisture, maybe the positive pore water pressure, or the change in matrix section. We also used a similar kind of sensors in the flume in order to track those data, the hydraulic variables, the hydrological variables. And we could see that during the event of rainfall, the volumetric water content is increasing, and also the pore water pressure, that is actually the matrix section is decreasing and the pore water pressure is increases for all the 5 tests. And for all the 5 tests, the loss of suction actually has caused in the instability. Here you can see the first test. So there was a tension crack developed, at a certain time after the rainfall is supplied, whereas there was no failure except for some amount of material at the toe. Whereas in this experiment, we have a kind of a slope failure at the toe part. And we believe this is what we see in the Himalayas when we actually approach the road and maybe we make the road excavation. The toe part is actually getting destabilized. Wherever the material, it's actually a kind of soil rock mixture, that is a mixture of rock fragments and fine soil. Similarly, the loss of suction derived strength, it's actually found to cause slope failures in also the other conditions where we have the slope angle for steeper 40 degrees, it's the overall slope angle. The upper section of the slope is still steeper than the lower section. And in this case as well, we did have the failure at the toe part. Okay, that is for the debris slide. And earlier also during my time as a postdoc in China, we did a similar kind of experiment, a much smaller flow for rainfall-induced debris slides in order to see whether the role of unsaturated soil mechanics is also hold true in runoff generating debris flows. Usually debris flow numerical models, if it considers the initiation of debris flows, it assumes the debris flow gets initiated or it will get initiated only in case of full saturation. Because as per Hortonian overland flow model, we think that the saturation is the point in which we consider the infiltration exceeded precipitation or the availability of rain that converts into a runoff. So that is the infiltration exceeded runoff. But that's not always true. If you look into literature of like hill slope based in situ studies of debris flow experiments by Professor Imezumi and all, so even under partial saturation, there are chances that there will be triggering of debris flows. This we wanted to test. And similarly, we designed a smaller flow with different debris flow deposits, whereas the grain sizes is not that much larger as we did for the Himalayan case. And in this case also for different initial moisture content, different uh, initial volumetric water content, different percentage of moisture, the same amount of rainfall is supplied, and we could see there is a sensitivity of initial moisture content. Now, for the debris slide case, what we understand from the traditional soil mechanics textbook, if we calculate the suction stress, so this is the suction stress, and if we use it for assuming infinite boundary conditions here for the two-dimensional cross-section, what we got from the experiments, we could see that there is a possibility of calculating the factor of safety that we did. And the schematic shows here that is there is increase in volumetric water content and reduction in matrix suction. That's found from the two sensors what we installed in the material, inside the material during the experiment. And whenever there is this further loss of suction and where this further increase in suction stress, we could see the safety factor of the slope, what we calculated under infinite boundary condition, it's actually going closer to 1. So traditional practice and will tell us if it's close to 1, we can assume failure. That's what we also did. And for different experiments, the factor of safety is plotted here. And with this, we kind of got an understanding that to an extent, also this will be subjective to the experiments or the material performed for that site alone. Okay, maybe for different site, different proportion of soil rock mixtures may have a different behavior. I definitely don't know what will happen if we mixture like different percentage of soil and different percentage of rock. We are continuously doing those experiments to understand more about the debris slide. But with this preliminary experiment, what we understand now is in the pre-failure stage, if we have a soil rock mixture slope of different grain size of debris, so the advancement of wetting front holds true, as well as the loss of matrix section is hold true. And the loss of matrix section may still be the reason why these slope failures are happening, even when we have a larger rock fragments within the slopes body. Okay, so the flume experiments what we performed revealed it actually contains the material from fines to gravel. And there are also a number of studies you can find, more than like 300, 350 available literature you can find for reduced scale flume experiments in soil. But if you think of like a soil rock mixtures, you'll find something like 50 to 60. And only very few studies have actually accounted for larger grain sizes. So those are actually reviewed in this paper as well. In the supplementary file of this paper, you can find all those studies who have actually considered to mimic the debris slide process in the laboratory. And what we got from this uh, from the interpretation of the results is the larger grain of debris contribute to the shear strength under total stress condition, but in dry conditions only. When the slope receives the rainfall, what governs the failure is the behavior of the fines. In the unsaturated as well as saturated, the fine material is the gluing one, which actually have the connection of the rock fragments. And as long as the suction stress is lower and the matrix suction is higher, the suction derived strength is actually available for the slope material, even in case of steeper slope. But when there is rainfall, there is this advancement of wetting front, then we do have the slope failures that is actually happening during during the rainfall. So we believe maybe this is one mechanism that is actually happening during monsoon in case of this rainfall-induced debris slides in the Himalayas. So, okay, we have got an understanding. So using simplified mathematical expressions, we can actually develop a numerical model. So there are many number of numerical models that is those are available for simulating rainfall-induced landslides, starting from Trigger's model by USGS Goat et al. So it's a very good model. And also there are many number of models, close to 10 to 12 models are available. And what our model, what we want to do is we have developed some models for shallow landslide as well as debris flows, and we need to test them whether it will be applicable for simulating debris slides and debris flows in the Himalayas as well. So this is the approach. So since we have got a confidence that, okay, so in 3-4 years time, we have got to know that this mechanism of unsaturated soil, it will also be applicable to an extent to also a mixture of soil rock medium, where the grain sizes is even more, where the D50 is close to 20. That's what the D50, what we used in the flume. So we developed an approach to actually use it for the catchment scale. So that actually considers the fundamentals of hydrological process, what we see in the two-dimensional cross-section here, as well as the geotechnical process, provided, as I already mentioned, that as we move across the scale, we are having the problem of complexity as well as in phase transition and also like dimension. So we cut across this dimension, it is a 1D model, and we cut across the phases, it is a single phase flow model. Okay, that's the biggest limitation this model is having. Provided it can be used for some purpose of understanding or to develop some thresholds for early warning. That's what we would like to see. And in the process of upscaling it to the slope to catchment scale, we started testing this model. This is the model what we developed during my postdoc time in SKLGP China. So that is for snowmelt induced landslides. So it has the all hydrological and geotechnical component of modeling precipitation induced landslide. Also, it can consider the rainfall induced landsliding as well. And we tested this model for one catchment in Niigata, that is fine. And now we are applying this model for Indian cases. So the accuracy of the model when we tested also, it's laughable, you can see, it's 59%. Okay, so 59% is the accuracy of the model, whereas we also got only 9 true positive, many true negatives, and so much of false positives. Okay, so the availability of good geotechnical data as we upscale the model from finer scale to a larger scale actually hinders the model performance. Irrespective of how accurate the model is developed in terms of the governing equations, the input data should be proper. But anyhow, we went with modeling this for the case study of post-seismic landslide. So he got it published. That's okay. And for Indian conditions, so if we want to develop or use the same model, so we also developed a debris flow model which considers the initiation of debris flows. There are many debris flow models which actually able to simulate the runoff very effectively considering different rheological parameters. But many models, except for some models which actually account for the hydrology, will not model the triggering of debris flows. So we also developed this model, and we applied these models for different catchments across the globe. And what I'm going to present now is the case of 2013 the landslides which happened in 2013. So for this, the study area what we chose was the Kedarnath catchment, as you can see here. So 120 debris flow happened between 15 to 17 June 2013 in this catchment. So this is a good case study for us to calibrate the model, and in order to understand whether the experimental based findings what we have developed through testing, that the unsaturated mechanism part is also applicable for landslides, then we have to use this case study for testing. So of course, we visited the site after like 10 years, close to 10 years after the disaster. We did collect some samples. So the D50 what we have got for the Kedarnath is like a 4 mm, whereas for the 2021 Chamoli Roorkee avalanche is 10 mm. Whereas for Wayanad, this is only has in this we did not fly any drone, or the larger particles is not accounted in this collection of this debris size. But to compare with the cases of debris flows that is happening in the Himalayas as well as in the Western Ghats, you can see the Western Ghats debris flow. The Wayanad one had the D50 of close to 1 mm. Okay, and we believe Wayanad is a different case. We believe the fine material present in the hill slopes during the Wayanad landslide was the reason why it got the enormous amount of erosive power to move large chunk of sediments. Similar to the glaciated part here, 10 mm, and the Kedarnath, it is like here. And so using this numerical model, our purpose was to run this model, okay, in accounting for the uncertainties, acknowledging the limitations, play with what we have. Then we know that for early warning of landslides in India, so we still rely on this intensity duration threshold that is available all across the globe, starting from Kane. And for different catchments, we had these lines. For Uttarakhand also, in the Mandakini catchment also. And using our model, we wanted to recreate and we wanted to find a meteorological threshold, that is the intensity duration threshold. So we used the model, so using the soil characterization, how much amount of sample we could do. So we did the model. As you can see here, these are the actual landslides that happened in 2013. And this is the laughable model performance, debris flow deposit from the model. Okay, model has widely said that here also debris flows, whereas there happened nothing. Okay, so that is the limitation of the model. So, but this is the best case calibration we have got for the model, and we compared the fan volume here with the empirical measured fan volume here. And once this is done, as we calibrate any hydrological model for the discharge, we believe this is the best set of parameters we can get from the calibration. Then we did some parametric studies considering different intensity and duration in order to see at what time of after a certain amount of intensity, at what duration of rainfall we are actually generating, the model is generating the debris flows. And that gives us a numerically model derived intensity duration thresholds. And this can be directly used along with weather forecast. Okay, if we have a forecast of this much amount of rain with a certain amount of duration that is going to happen in the coming hours, then if the threshold is actually reaching the intensity duration threshold derived for this catchment, that's a hydrological boundary, then it is possible by us to give an early warning signal. This is widely practiced all across the globe. In India, it is in development. As I already mentioned, NLFC is actually doing it very well. And so for the Kedarnath case, so the model derived intensity duration threshold line is here. And for the 2021 Wayanad debris flow, this is from the actual data. So it happened with an enormous amount of rainfall. So it sits over here. And this intensity duration threshold also has a limitation. Now we are moving from, let's say, fundamental geotechniques to early warning systems, where we actually move into meteorological and hydrometeorological thresholds for early warning of rainfall induced landslides and debris flows across the Himalayas as well as in the Western Ghats. And so this is a sketch of available information. The list is not exhaustive. So there are different nations which use for informing people in an early warning system using a meteorological threshold that is mainly based on the characteristics of the rainfall that is going to create a landslide. So that is the meteorological threshold. And there are few nations which actually rely on hydrometeorological threshold based services, that is mainly accounting for the soil moisture or the real time condition of the ground, or an any index value, that is the soil moisture. One such thing is the soil water index, which is widely practiced for sediment related disaster early warning in Japan. So this is the schematic that is available from this manuscript in Landslides Journal. So in earlier days, it was for every 5 kilometer by 5 kilometer grid. Now Japanese government has established for every 1 kilometer by 1 kilometer. There is a meteorological threshold. The threshold line looks like this. And we do have an early warning or early forecast of rainfall that is going to happen in an hourly scale. So that is at the 60-minute interval. And the soil water index, that is a hydrological model based parameter that is calculated, is plotted in the x-axis, and then in the y-axis you have this hourly rainfall. And for every grid, if you have this information, the snake line is going to exceed, then there is a chance that occurrence of a sediment disaster and non-occurrence of a sediment disaster. Like this, the line is also further calibrated. For this, the hydrological understanding of the catchment is the fundamental, and this is a tank model developed from Okada Shinsei in 2001, and it is actually widely practiced in Japan even now. And there are some hydrological model-based parameter here. It can also calculate rainfall, and we introduced the snow melt also into this model. And we actually established thresholds for many regions across the Hokkaido prefecture in Japan. So this is the operational of the debris flows and slope failure. And why we are interested in this one is, okay, we had some kind of understanding of debris slides and debris flows that gave us some fundamentals. Okay, this is how we believe that the landslide is happening during a rain in the Himalayas. If we believe that, then what next? If we can use our numerical models or our process understanding in order to develop some thresholds that will be useful for the national landslide forecasting system, then that is what we need to see. So this is the schematic of how the Japanese government is actually giving the early warning information. It is actually taken from this paper. And during my time as a PhD student and postdoc in Japan, so we developed this model to check for improved thresholds for based on hydrometeorology, which also include the snow melt. And presently at IIT Roorkee, after I joined here, so we are trying to make it adaptable for Himalayan conditions. So here, if we see the 2013 Kedarnath case study, that's the one we are still working on. And we tried to collect some different hourly rainfall data sets, what might have happened between 15 and 17 2013 in Kedarnath, or also the other regions across Uttarakhand. You can see here, this is the inventory of landslides. There were more than 6,000 landslides all across Uttarakhand. So this is the Mandakini catchment, the Kedarnath is here. The biggest disaster, the 120 debris flows, what we simulated in the earliest study is here. And all across Uttarakhand, we had landslides at that time. So we need to test whether the soil water index, what we actually believe that it is very much working well in Japan, will it be applicable for like forecasting landslides in Uttarakhand, provided we do have the understanding of the thresholds and as well as the mechanism of debris slides and debris flows in the Himalayas. For different input rainfall data sets, as well as from numerical weather prediction models, and also some reanalysis data sets that is available from IMD, and that is the IMDA from NCMRWF, and also the global precipitation dataset GPM rainfall. So these are the soil water index that is actually calculated based on the hydrometeorological threshold. As we could see, this is an extreme rainfall condition, even which the superimposition of the soil water index threshold over much amount of large areas of debris flows and landslides all across Uttarakhand. So, and we got a confidence that it is possible by us to use the soil water index, provided we know the mechanism of landslide and we know the hydrological process behind how these landslides are happening. So we could use the soil water index. And if we calculate the threshold as what studies have done for cases in Japan, so this is the critical line. So we do not have an existing critical line because we are doing this for the first time for Himalayan cases. For Indian cases, we take reference from the existing general critical line that is widely adopted across literature in the Japan. And for different data sets, this is the hourly rainfall, and we could see that it is actually nearing the critical line, or one data set, maybe this is an overestimation of the rainfall, because this is not bias corrected. And this can actually give us an indication of a landslide at least before like 6 hours, 8 hours, if we have the rainfall forecast. So that is where we are now. So we tried to understand the mechanism of debris slides uh, in Uttarakhand, and we kind of tried to expand it over the scale in order to give the National Landslide Forecasting Center in India or any other agencies, if they are required of these thresholds to be developed. Now we have a method that this method actually accounts for some kind of process understanding of hydrology as well as geotechniques from the laboratory, and as well as it is expanded to the scales at the catchment, and it is applicable over a larger region as well. But this is still in a very, very preliminary stage, and we are a small group, just started working, just I said, like 4 years ago. We could only do this much, and it is a long way to go, provided understanding of the limitations of the methods what we are using, and then the understanding the limitations of the course we are developing. So the biggest thing, as also Professor Reddy has mentioned, that the importance of interdisciplinary nature of the problem. An engineering geologist alone or a geotechnical engineering guy or a person alone cannot solve the problem of landslides in the Himalayas. It's a disciplinary, multi-dimensional problem. So we have to put our efforts. So we are contributing in terms of like engineering geology and geotechnics, and we hope that we'll have like very good performing early warning systems for sediment-related disasters in the Himalayas. With this, I'm finishing my presentation. This is my group at IIT Roorkee, and we have a laboratory page here. If you scan this, it will take you to the lab. And I thank you all for patiently listening, and I'm open for some discussions as well. Thank you.
Yeah,